Okay, so how many remember arc length in Calculus 2? Math 182, seeing arc length. Okay, Christopher remembers it. I hope more than just one person. All right, good. Robin, John, and Eric, and you know you and Ryan, and you learned a formula. You learned a formula for arc length. Well, there's an analogy. So, like, this was the formula that you learned. How many recall this formula in Calculus 2? Okay, Robin remembers it very well. John remembers it. Ryan, absolutely, absolutely. So, what do you think for the, and that would cover a curve, a space curve in two-dimensional space, that arc length formula there, formula 1. What would we need to have a formula for three-dimensional space? What would we need to add here? A z component, an h of t. Very good, very good. So, okay, no problem, no problem. There you go. That's the formula, the corresponding arc length formula when you have a space curve in three-dimensional space. There it is. So just like the distance formula can be extended for three-dimensional space, the arc length formula has a natural extension for three-dimensional space. Okay, and it's really not a big deal finding the arc length for space curves. Man, is this disappearing again? Hold on, I got to bring it back. Hold on. Be sure to, give me a click or like a chat click if this book doesn't show up. If you're not seeing the book on the screen, let me know, okay? I appreciate it. Okay, so and this is the standard short-term definition for arc length. You've seen that before. So in example 1, they want you to find the length of an arc of a circular helix with this vector equation from the point 1, 0, 0 to the point 1, 0, 2 pi. Okay, so naturally, we'll get a formula for the length of the derivative vector. And it turns out that that this derivative vector, the length is constant. I want to say the magnitude of the derivative vector, the length, is a constant. And so to apply the arc length formula, all we need to do here, let me see if I can have, all we need to do is just, apply the formula. And incidentally, the t goes from 0 to 2 pi because when t equals 0, you're at the point 1, 0, 0. And when t equals pi, you're at the point 1, 0, 2 pi. Okay, so the length of this arc is 2 times the square root of 2 times pi. And we can see the arc. We could graph that arc, right? We know how to graph a space curve using MATLAB. We have the actual length of that arc. And a helix is actually a very nice space curve, a very famous space curve. It's very important in biology, a helix. Why is that important for biology? in chemistry? DNA, that's right, Christopher. DNA is composed of helix or helices, I should say. So, how long is the helix? How many have heard that a helix is this long and it's like almost 2 meters in length? A little helix in your blood. I got to be careful, not your. Well, yeah. I guess if you stretch it out, how many have heard a helix is? I believe is it almost 2 meters long? A DNA strand. How many have heard this? Okay, Eric's confirming that. And so how do you find the length? Well, you better have an arc length formula, right? All right, so and you may remember in calculus 2 when you use the arc length formula, a lot of times, you have to deal with that square root, right? You have to deal with what you're going to get under the square root. And sometimes you have to make a substitution. You have to play around with the expression, in like here, they use the trig identity to say sine squared plus cosine squared equals 1. But sometimes, that won't work. But sometimes you have to maybe the expression under the square root, you can factor it, and then, you can write it as a quantity squared, and then the square root of that quantity squared comes out. So what I'm trying to say is, in certain instances, like for instance in the web assigned homework, if they're saying find the exact length of the curve, what they want is an exact answer, simplified radical form. They don't want a decimal approximation, and it won't take a decimal approximation. So in those cases, you have to just, figure out how you can write the expression under the square root as some quantity squared, or comes out as a constant like it did here. You just have to just be inventive, so to speak. How many recall that with arc length problems? You have to be a little bit inventive sometimes to get the answer. Okay, Ryan remembers that, and so it's the same here. But what we're going to do, I want to look at a problem where we're actually going to have to use numerical integration to get the arc length. So let me look at this. We're going to look at this problem, and then I'm going to be able to give you a little time to work on some classwork. But let me go ahead and bring this problem up. Let me see. Okay, I guess I got to download the file. So just give me a moment here. I could go for a Big Mac hamburger right now. I mean, I'm feeling good, but how many kind of have like a little bit of hunger feeling? Like maybe they could go for a Big Mac or a Whopper or Chipotle, something in Chipotle. Okay, is anybody? Okay, okay, John. All right, enjoy. I hope it's Chipotle. Or all right. Okay, I'll tell you too. I'll tell you the Taco Bell makes really good burritos. Some of those burritos. How many like Taco Bell? Here, any Taco Bell? I don't mind this is on the recording. It's cool. All right, Robin's a Taco Bell guy. All right. I never tried Taco Bell. John likes it till recently, but those burritos are darn good, and they're not too expensive either. All right, well, let's go ahead and take a look at this example here. Okay, so I try to pick an example that's going to make you think and be helpful for homework and all that. So, all right, let me give you a moment to copy this down. Okay, so in this problem, what we want to do is we want to find, correct to 4 decimal places, the length of the curve of intersection of a cylinder and a plane. Okay. And incidentally, this cylinder here, this cylinder, it's really an elliptical cylinder. It's got to be an elliptical cylinder. It can't be a circular cylinder. Hold on here. Hold on, I have an idea. I'm gonna, one moment here. One moment. I'm trying out my my new writing tool. Yeah, that'll work. It's an elliptical cylinder. So it's like a, well, the cross section of the cylinder is an ellipse. And so does this elliptical cylinder here, does this elliptical cylinder here, does it go sideways or does it go up and down? What do you think? It goes up and down. Good, Ryan. Good, Christopher. It's an up and down. There's no Z. That's right, Christopher. It's an up and down elliptical cylinder. So you have to picture in your mind this cylinder goes up and down, and then you have a plane that cuts the cylinder. The plane cuts the cylinder. So wouldn't the plane cut the cylinder? Wouldn't the cut on the cylinder be a space curve? When the plane cuts the cylinder, wouldn't the intersection be a space curve? Yeah, absolutely. And so we want to find, well, first of all, in order to find the length of the curve of intersection, we need to figure out, you know, what is, hold on, let me try it here. We need to figure out what is R of t? What is our space curve? What are its x, y, and z components? Okay, and so let's go ahead to the next page. So we need to find R of t for this space curve C. That's the intersection between the cylinder, that elliptical cylinder, and that plane. And what I've done is I've drawn a little picture of the situation here. Okay, and let me give you a moment to just kind of copy down up to this part. Okay, let me give you a little time to get that copied down. Okay. Okay, so what I've done is I've drawn this circular cylinder. Okay, this of course is the, the origin there. And I've drawn the circular cylinder, and the plane cuts the circular cylinder right along this curve here. Now notice, and I'm sorry, I want to try to get it. Hold on. Hold on, Claire. Get that out. I'm going to go back. Now hold on here. I'm going to go back to the mouse here for a little bit. Okay, there's the curve, space curve. And you'll notice that protruding from the center, the center of the space curve, the region inside the space curve, I've drawn a vector that has components 1, 1, and 1. Okay, why do I know that orthogonal vector there, this orthogonal vector, maybe I'll put it in blue. How do I know that this orthogonal vector has components 1, 1, 1? How do I know that this, man, it's hard because I gotta switch back and forth, How do I know it has components 1, 1, 1? That's right, Christopher. Look at the equation of the plane. The equation of the plane is 1 times x plus 1 times y plus 1 times z equals 2. That means the normal vector, perpendicular vector to the plane, has components 1, 1, 1. Well, it's the plane x plus y plus z equals 2 that cuts out this space curve here. And so from the region inside the space curve, that region, the vector perpendicular to that region would have those components, 1, 1, 1. So, it's just something that I like to, put in there for you. It helps also give the picture a little perspective. Now, also, just to help draw the picture, if I look at this equation, we know equation of ellipses, how to identify x-intercepts and y-intercepts. And the only reason, of course, this is an elliptical cylinder, but the only reason I find these values is just to help tell me which part of the ellipse is fatter and which part of the ellipse is thinner. So would this, I should say, which part of the elliptical cylinder is fatter and which is thinner? So is the elliptical cylinder fatter in the direction of the y-axis or the x-axis? Is the elliptical cylinder fatter in the direction of the y-axis or the x-axis? The y-axis. Okay, so we do every little thing we can do to help us have a feel for the situation at hand. Okay. All right. So hopefully you have a picture in your mind of this situation we're dealing with. Now, one thing we'll note also that needs to be noted: if you take the projection of the space curve, that red space curve C, onto the xy plane, then you're going to get, of course, a different space curve. And this space curve would have components cosine of t, 2 sine t, and 0. Of course, the z component 0, you're in the xy plane. But why are the x components cosine of t and the y components 2 times the sine of t? Well, if you consider those components and you substitute them in for x and y in the elliptical cylinder, you're going to get cosine squared plus sine squared. You're going to get a 1. Okay, so basically the elliptical cylinder, which was originally 4x squared plus y squared equals 4, that equation can be rewritten as x squared over 1 plus y squared over 4 equals 1. And so if we plug in x equals cosine of t and y equals, this should be a 2 here, little typo, this should be y equals 2 times the sine of t. If we plug those in the elliptical cylinder equation on the left side, we get a 1 on the right side. Okay, so I mean, the elliptical cylinder, I want to say this the right way, the space curve R1 of t, its x and y coordinates have to obey the coordinates of the elliptical cylinder. Okay, because it's just a projection of the elliptical cylinder. So the x and y coordinates have to obey they have to obey the elliptical cylinder equation. And by letting x equals cosine of t and y equals 2 sine of t, they do. Because you get the left side will equal the right side, which is a 1, and it has to be a 1. So that means this is the correct parameterization for that R1 of t. Now there's a reason we're doing this. Remember, what are we trying to do here? Well, ultimately, I mean, what we want is the parameterization for this space curve here, right? I want the parameterization for this space curve. What's the only difference between the space curve R of t and the space curve R1 of t in the xy plane? What's the key difference? What's really the only difference between those two space curves? The z. Very good, Ryan. So the excellent. The x and y components for both space curves are going to have to be the same, right? They're going to be the same. So the fact that we found the x component for the space curve R1 of t in the xy plane and the y component for the space curve R1 of t in the xy plane, those are going to be the x and y components also for the space curve R of t. And so that means then that R of t, the parameterization would be cosine of t, 2 sine of t, and then, well, z is equal to 2 minus x minus y, hence z of t has to be 2 minus cosine of t minus 2 sine of t. And now we have the parameterization of the space curve that comes from the intersection of that elliptical cylinder and the plane. Okay, so sometimes you just have to be a little bit inventive in getting your space curve, and you'll have a problem like this in your section 10.3 homework. For Sunday, but you know, you'll have seen a similar problem, so that's nice. Are there any questions up to here? All right, well, now what we want to do is we want to apply the arc length formula. Remember that we want to find the length of that curve of intersection. So, okay, I have to compute the derivative of my space curve, and then I'm going to apply the arc length formula. Okay, so you add you square each of your derivatives of you square each of the derivative of the components, square each one of those, add them up, take the square root, and that gets you down here. See, this problem, the parameterization, I was thinking maybe you could use a little guidance on how to get that parameterization. And how many are kind of glad I'm covering this problem? Okay, Robin is. All right, John is. Brian, excellent, excellent. All right, so now what happens is are there any questions down to here? Okay, well then now what you have to do is you have an integral. You have an integral to solve. And we're going to let t, if t goes from 0 to 2 pi, that traces out the space curve just one time, right? You have to have limits so that the space curve, if you're looking for the length of the space curve, you want it traced out just one time. Okay, so if, for instance, I had chosen limits from t equals 0 to t equals 4 pi, that would trace that space curve out twice. But like, you know, we only need to trace out the space curve once because we want the length of the space curve. So we get this, and offhand, do you think it's possible to find the antiderivative of the square root of the quantity 8 cosine squared t plus 2 sine squared of t minus 4 cosine of t sine t? Do you think offhand it's possible to get the antiderivative of that? I mean, how many of you would not want to try that one? You know substitution, integration by parts, partial fractions, trig substitutions, but yeah, I mean, I agree with Ron. I don't think any of those would break down that integral. So we need to get a decimal approximation. Yes, Eric, I agree. So, well, we need some MATLAB code. I want to show you the program that's gonna handle this. That's gonna handle this for you. So may we hold on here. Hold on, did I lose you all? Whoa. Sorry, Dr. Duty's back. I'm back. I'm back. Somehow I got thrown out for a minute, but I'm back. So all right, let's continue here. So what we want to do is we want to verify that the length of this space curve is 13.5191. And to that end, what we want to do is we want to, hold on here. Now hold on, did I get a, all right, hopefully everything's good. Can everybody hear me okay? Can everybody hear me? Good, good. All right, great, great. All right, so, all right, let's go ahead. Are there any questions before I go to the program? Are there any questions at all? Okay, all right, so let's go into, all right, into Blackboard. Can everybody see Blackboard okay on the screen? Okay, great. Thank you, Ryan. Thank you, John. Ryan, thank you. All right, so again, where do you think you're going to go? Where do you think you need to go to find what we need here? We need a MATLAB program, so we're going to go to MATLAB programs. We'll click on it. Click here to see helpful MATLAB programs. This relates to arc length, section 10.3. This MATLAB program will help you numerically integrate a function of one variable. So I'm going to click on the program. Okay, and then I'm going to open it up. So I'm bringing up MATLAB. Okay. So now let me go into where I need to go here. All right, can you see the program all right on the screen? Okay, good, good. Thank you, Ryan. So when you do integration in MATLAB, well, you know, there's multiple ways, but here's the way I chose. I define my symbolic variable t, and then the int stands for integral. Int here stands for integrate. What are we integrating? Oh, we're integrating the square root of what? Of 8 cosine squared t plus 2 sine squared t minus 4 cosine of sine t. That's what we're integrating. Oh, what are we integrating with respect to? We're integrating with respect to t. Oh, okay. What are our limits? T goes from 0 to 2 pi. And then in the end, I don't want a symbolic answer. I want a numerical answer. So once I get my answer, I'm going to use the command double to convert the symbolic answer into a numerical answer, to a decimal. Okay, and so on that note, I'll copy the code here. I can make this up a little higher, and I will paste it here on my command line. And there you go, 13.5191, and that is the length of that arc. All right. Are there any questions on the MATLAB code there? How many is this their first time doing an integral using MATLAB? Okay, good, good. Ryan, Christopher, Robin, Eric, and Jamal. All right, quite a few of you. So So of course, what I try to do, it's very easy to make a mistake when you type your code. So what you always have, what I try to do is, there are a lot of parentheses. There's a lot of grouping symbols. So I try to space my grouping symbols out a little bit so everything's not so condensed. Okay, it's just a technique that I've found helpful. Okay, all right, and also what I'm going to do here, if I want to have more decimals, and by the way, there's a thing you can do called clear vars. If you want to clear your variables from your workspace, you can hit clear vars. And that's probably not a bad idea. Probably not a bad idea to include that in the code, actually. Probably not a bad idea to include that command. Because sometimes what happens is when you work a lot in MATLAB, you have, every time you create a variable or a value for a variable, it stores in a workspace. And sometimes you inadvertently will you'll think you'll have a variable you haven't defined, but it's been defined before, because by the same letter or something, and then it causes confusion. So I'm going to use clear variables, and I'm going to do CLC here. And hold on. All right, good. Everybody's seeing it okay. I love MATLAB. Paste, enter, there you go. And by the way, if you want a longer answer, more decimals, you can use format long. Format long. And then you can bring the command back, hit enter, and how about that? How many like that answer? I like that answer. It's still not an exact answer, though. Not in simplified radical form. Okay, so, but how many think format long's pretty cool? Yeah, so, you know, WebAssign with now WebAssign, of course, usually tells you how many decimal approximations that you need. But I'm just saying, for maybe your other classes, if you ever need accuracy like that, maybe like an astronomy or something like that, physics class, hey, you know, use format long. Okay, are there any questions on the code, MATLAB code? All right, and we now have justified. We now have justified the answer here. Okay, are there any questions? Okay, let me stop the recording.